Okay, we are looking at description logics, and we have looked at the structure matching algorithm, which is a algorithm which takes two descriptions and answers the question whether one of them is subsumed by the other or not. And we had sort of informally argued that it is a very cheap way of doing things, in the sense that you only have to inspect the two descriptions, and based on that inspection you can answer this question essentially. Later on we will just have a glimpse of languages which are also description logics, which are more expressive than the current one. We will look at what we cannot say in this. Maybe you should think about that. What are the kind of descriptions that you cannot express using the language that we have, and we will try to see whether there are languages which allow you to do that, and how much of a cost we have to pay in terms of the subsumption question, answering the subsumption question. But given that we have a module which will answer the subsumption question, we want to look at an algorithm which will automatically construct a taxonomy, and this is independent of which language that we use. As long as we can answer the question that is D 2 subsumed by D 1, then we can have an algorithm for constructing a taxonomies. So, this is what we want to look at now. Okay. So, first observe that subsumption is a transitive relation. And the taxonomy is a partial order. And you must have studied this somewhere, that you can always depict partial orders by Hasse diagrams, which in which you do not represent the transitive edges, you only represent the parent child in the subsumption hierarchy edge, and you always draw the parent above the child essentially. So, typically a taxonomy would look like this. So, you have thing at the top, and then it may have some children, they in turn may have other children, and this process goes on. So, when we draw the taxonomy, or when we draw the Hasse diagram for the taxonomy, we are not drawing implicit edges. So, these edges are explicit, but they may be implicit edges. For example, this just to illustrate, these are implicit. Now, we look at a task which we call as classification. The sense of classification is a little bit different from what you might use in pattern recognition. By classification we mean, given a new concept, let us call it D, place it in an appropriate place in the taxonomy. So, today we are in this class we are going to look at this algorithm for classification, and by this algorithm we mean that you have an existing taxonomy and suddenly you get a new concept. Where should you place a new concept in the taxonomy? So, for example, maybe the new concept should sit here, and then maybe you have to establish new edges and so on. So, the task of placing it in the appropriate place, so that it is a child. So that it is linked to a parent who is its immediate super concept, and there is no super concept in between, and likewise whose child is a most general sub concept that you can think of essentially. So, anyway, we will look at this algorithm in a moment, but if you have such an algorithm, then you can imagine that you can actually construct your entire taxonomy using this algorithm. You start with an empty taxonomy, take the first concept, insert it into the taxonomy, take the second concept, insert it into the taxonomy, and keep repeating this process till you have constructed the taxonomy. So, in general we are looking at a stage where you have some concepts already in the taxonomy and you get a new concept, and then we want to place it in the taxonomy, and we are going to use this oracle or this module or this function which answers the question whether given two concepts which whether one of them subsumes the other or not essentially. So, our approach to classification is as follows. That given some taxonomy, construct or determine or find, let us say determine the set S. So, given a new concept D and a taxonomy, let us call it tau, set of concepts S of most specific of D. So, the first task is to determine the set of most specific subsumers of D. So, I do not know whether I should really go and try to define this formally, but I imagine that you can do this because you have looked at sets and relations and partial orders and so on. So, basically the set of most specific subsumers of D are those that subsume D and who have no children who subsume D. You can say it more formally, but I will just leave it at this here essentially. So, let us say this is our taxonomy. We start with the thing or top concept, and then we have this concept D which we want to place somewhere, and the first thing we do is find a set of concepts S and we will look at how to do this in a moment, which are the most specific subsumers of D essentially, which are nodes in the taxonomy essentially. Then the next step is to determine the set G of most general subsumes of D. So, just as we define the most specific subsumers, we can define the most general subsumes. They must be subsumed by D, but they must not have any parents which are subsumed by D essentially. So, we can define it like that. I will not write it here. So, let us say this is a set which obviously will be below the node G, below the node D essentially. It is possible that the two sets are not disjoint. It is possible that they have a element which is subsumed by D as well as which subsumes G essentially. What would that mean? Supposing these two sets S and G are not disjoint and they have a common element, and the common element subsumes D as well as is subsumed by D. That means D is already there in the taxonomy, and that element is actually a description of D, or D is a description of that element essentially. So, it is almost there, in which case of course, we do not have to do anything essentially. If S intersection T, sorry, I keep writing D, G is not equal to phi, then do nothing essentially. I mean, do nothing in terms of constructing the taxonomy. Maybe you can attach the label if you have a new label or something like that for that essentially. So, now the situation that I have drawn is a situation where they are not disjoint. They are disjoint, which means they do not have any common element essentially. Now, it is possible that not only possible, it is very likely that they will have links going from those elements to these elements, because before we inserted D into the taxonomy, they had children, and some of those nodes in G would be children of those nodes in S essentially. So, the next step is to break all existing links or edges from S to G. If there are edges, then remove them. So, the edges that we are talking about are the ones which are depicted in blue here essentially. And finally, add edges from S to D and D to G. So, let us say the edges are subsumption relationship, which means, so if I show this in red, you establish an edge between every element in S and D and between every element in G and D as well. So, you remove the blue edges and add the red edges essentially. That means, we have now put this concept D that we had to insert in the taxonomy essentially. So, that is a high level algorithm. Now, let us look at how to construct S, and then we will see how to construct G essentially. So, I will just describe this algorithm, and we will see, maybe we will write it, or otherwise you can write it yourself essentially. So, initially construct a set P you might say possible parent and what does P get? Initially P gets the top element thing. So, you start at the top of the taxonomy with the thing and add P to that essentially. Okay, so let me write this a little bit. Then you pick a node n from P, and when we say pick a node, we also mean remove it from P. Now, if there are two possibilities that either this node n subsumes the concept D. So, remember that we are given D and we want to place this D into the taxonomy and we are constructing this set S with respect to this node D. So, there are two possibilities that this node n either it subsumes D or it does not subsume D. If it does not subsume D, then we are not interested in it, because it can never be a parent of D, but if it is if it subsumes D, then it is possible that it could be a parent. Now, the only question we want to answer is it a parent or is it an ancestor, which means is it an immediate super node or is it somewhere high up or removed from D. So, if D is subsumed by n and we already have a procedure for us answering this question, then if there exists a node C which is child C of n. So, if there exists a node C which is a child of this node n and D is subsumed by that child, then add all children of n to P. Okay, notice you can we are adding all the children of. So, what is the situation? Let me draw it here. We start with thing, then we generate. Now thing subsumes our concept D, because thing subsumes everything. So, we add all the children of thing into the set P. So, this is a set P that I am constructing. Now, I look at each of these nodes one by one and ask the question that does it subsume D or not essentially. So, let us say that this one does not subsume D. Let us say this notation stands for this, then we simply just throw it away, we are not interested in it in any more. Likewise, let us say this one is also not does not subsume E. So, we throw it, but let us say for this node there is a child C which subsumes D, Then what do? I add all the children to P. So, this red circles are the nodes in P. So, let us say this cross means that I have thrown it away essentially, and let us say for this also I add the thing. So, I of course remove it from P. So, what is left in P is all the children of some nodes essentially. Which nodes? Which subsume D. Now, whether to add all the children to P or not is a question of algorithm design. You can think of adding only those children which subsume D, but it does not really matter. For each child you have to subsume, you have to do this check at least once. So, you can do it either now or later, it does not matter. So, we continue this process. So, let us say all these elements do not subsume D. Let us say my D is somewhere here. So, the first thing you will observe is that this algorithm, even though it is looking at the entire tree or taxonomy or whatever you want to call it, it is not going to inspect the entire tree, it is only going to inspect, it is going to dive into that part of the tree which subsumes D essentially. So, it is not going to be very complex in terms of complexity essentially. So, all the nodes that we have crossed out, their children will never be seen essentially. So, let us say we do this process continue, and then let us say this gets thrown away for some reason, and let us say this gets thrown away. So, we are left with these 6 essentially. Let us say this also does not, this thing just to make our life simple essentially. So, we now have nodes which subsume D. Okay. The set P contains possible parents, these are nodes which subsume D or which possibly subsume D, because we have not checked for every child whether it subsumes or not, but we have added them to P or not essentially. But we are going to ask this question at every point, every time we pick a node n from P, we are going to ask the question that does that node n subsume D, only then we are going to proceed into the rest of the algorithm essentially. So, we are interested in only those nodes which D. Now, if they have children which subsume D, then we are going to add all the children. If they do not have, so this is a else part. Add n to S. I must say that somewhere you must initialize S to empty set, and then the moment we find a node n which subsumes D and which has no child which subsumes D. So, for example, the children could be below D essentially. So, something like this. If this is the situation, then none of them subsumes D because they are all below D. So, this is the set that I am constructing, sorry S finally, and when you look at the children, I would not have added them to S anyway, because it is only if the child, if at least one child subsumed D, then I would have added the children, and even if I had added some children there, they would not subsume D and they will get thrown away essentially. So, this is the process by which we construct the set S essentially. We start from the top and we keep sort of focused towards the node that we are interested in, which is this node D, and we try dive down towards the parents of D essentially. Then finally, we have to construct G So, given the node D and also given S essentially. So, we have already constructed the most specific subsumers S, and now we are interested in the most general subsumees G essentially. So, this says that initialize G to S, you start with all those nodes S. If n is subsumed by D, then add n to G. So, I should have said pick a node, pick from G and remove it. So, essentially what we are interested in all those nodes which are subsumed by G essentially, which are subsumed by D essentially. So, that is a test that we do, that if n is subsumed by D, let me say retain it. Maybe I should write it slightly differently. So, maybe we do not remove it there, else remove it from G and add all of n to G. So, essentially first we are finding all the nodes which are subsumed by D essentially. So, we start with the set S. If it is subsumed by D, we keep it there. If it is not subsumed by D, we throw it out, but add out all its children, and we repeat this process for all the thing that we keep adding to S. So, eventually of course, we will exhaust the subtree below the node the set S, and then we would have constructed some G, but this G is not the one we want, because it includes all subsumees. We want only the most general subsumees. So, after this whole process is over, if there are two nodes C 1 and C 2 in G, such that C 1 subsumes C 2, then remove, or C 1 is subsumed by C 2, then remove C 1 from G. So, we do this process of culling out all children of, we want only those nodes in G which are the most general. We are not interested in their children, because they will naturally be subsumed by D. If a node in is subsumed by this given node D, then its children also will be subsumed by node D. So, what the process that is happening is that we started with some S, and then essentially we started adding children of these S. So, D is somewhere here, let us say. So, if a child is not subsumed, we just throw it away, but if a child is subsumed, we keep it. So, likewise, let us say we throw this away, we keep this, then we keep this, and let us say this is the end of our tree essentially. So, let us say we throw this away. So, we are left with this set at the end of this. From this we remove anything that is subsumed by another element of G. So, which means, so let me depict this in blue here, remove this thing. So, we remove this because it has a parent in G, remove this because it is a parent in G, remove this remove this, remove this, remove this. So, in the end we are left with these nodes which form G essentially. So, once we have S and G, we know what to do. We basically inspect the links between S and G, break all the links and establish new links between D and S and D and G essentially. Okay, so, this gives us this algorithm classification which places a new concept in D. So, what do we mean by that? That we have this new concept D and we will add these links and then we have a new taxonomy essentially. So far we have not spoken about individuals, because we are interested in individuals and we will do that in the next class and we will see about what to do with individuals and where will they be placed in the taxonomy essentially. Okay, so I will stop here and we will take up individuals in the next class.